Welcome to the Valve Studio. My journey to Tonehenge continues. I've been working on and off for about 5 days. I got a lot of parts in. I'll go ahead and show you each of those parts and some things that I had to revise along with the design. And we will show you where we are. First of all, I referred to my Openbuilds Workbee 1010 last week as portions of it had open beams. That's not correct. These are just C-beams, or they are straight 2040 extrusions. I have a box of open beams back here that I bought about 6 years ago. I don't know where that came in, but I'm going to make sure I call this my Openbuilds equipment. All right, first thing is, a few days ago I posted a picture of these things. These are my NEMA 23 integrated step-servo motors. These are 2 Newton meters. The motor driver's up here. Encoder and driver electronics are back here. This thing has a resolution out to micro step out to almost 50,000 steps per revolution. We're not going to run it at that rate. We're actually going to run it down. I think I end up running it down about 1600. So got these babies. These are the NEMA 23s, but when they went up to 2 Newton meters, they increased the shaft diameter here to 8 millimeters. So my 1/4 inch to 8 millimeter shaft couplers that came with my 1010 kit aren't going to work. So I bought these jaw couplers. This is 8 millimeter lead screw, but it's not actually 8 millimeters. It's something like 7.85. And because of that, the clamping action of these is not, doesn't have enough travel to actually pull the clamp part of this in to grab a hold of that lead screw. So I needed some shim stock, so I called a friend of mine in town, and he has some. And I showed him what I was doing, and he says, "No, you'll never get it together with shim stock. You should just use a piece of paper." I was like, "Really?" And he goes, "Yeah, just a piece of copier paper. It's about 3 mils, and that'll work fine." It turns out that he said that paper at that thickness it's not really compressible, so it'll work fine. And sure enough, he was right on the money. I was able to get this to clamp down just fine. I did add a couple of extra set screws to this. I ended up tapping my jaw pieces with an M3 hole, and then I just used a regular cap screw in here, and then I can clamp onto the flat spot on my stepper motor. And then I went ahead and cooked on this side as well, so I can, have an additional clamping force onto the lead screw. Got my limit switches in. They are somewhere here. Got a bunch of these. I got the kind of a little roller wheel on them instead of just the flat static arm. And I got the right hole spacing so that I could use the limit switch mount bracket from the hardware design. And over at Openbuilds, they have all their parts, all the CAD models for their parts in a zip file. So I downloaded that, and I opened up the limit switch mount bracket, which looks like this. Theirs, if you buy it from Openbuilds, it is probably aluminum, 3 millimeter aluminum that's anodized. This is just straight PLA. It's actually still pretty rigid, even at 3 millimeters thick. No, that's probably 4. Screws can go in either way. This is actually pretty handy, but it did bring up a good point about some of the aspects of this design. So, like this leads for the X-axis limit switches. They're meant to mount the design mounts on this piece of extrusion here, and because of the distance of this and the way, now I got the same kind of switch that they have in the design. When you put this in there, it turns out that let me use this one. It turns out that the roller wheel doesn't make a center of point contact with the back of the X gantry. It kind of does, but it could be better. So I'm going to mount my limit switches up here because this distance here is set perfectly for this limit switch and this gantry plate to come in almost near 100% contact with my wheel. And I'm in the middle of the plate. I'm not near the edge, so that's good. I'll talk about it a little bit more about the design, about that part of it in a minute. So I got that going. The other thing is this particular design, these little holes on the back of these limit switches are 2.3 millimeter diameter. That's the ID, and but this is got a lot of plastic around this hole, so it took an M3 thread really nicely, and so I didn't need a retaining nut on here. You just thread it right in. I did use a tap, and I tapped these out to 3, and a regular screw. My socket head Phillips screw. No, whatever that hex screw will fit just fine. There is some issue though with the collision. The heads on my screws collide with the extrusion itself. So these things come with an oval in the mount plate to put my M5 screw through to mount it onto the extrusion. But I'm right at the edge of where I can mount this, and so my screw actually comes in full contact with this and keeps me from I'm not able to move this around and have any flexibility. You know, I have this flexibility, but I can't actually move it up and down at all. So, but you have to have it at that same thickness in order for this switch to work right. So it works out that it's going to work fine for what I need. Okay. Let me see. Screw head. Okay. Mount plate size. Screw. Oh, okay. Let me see. It turns out that I needed some of these shaft couplers. Not couplers, but these lock collars for another project. I got them for 8 millimeters as well. Now, because I used jaw couplers instead of the coil cut ones, my lead screw can come out of the jaw pretty easily. So it really requires that I have really good lock collars on my lead screw. So this extra bag I'm going to use, I got these for like $1 over Openbuilds a piece. I'm going to use 2 collars on each end to really kind of secure that lead screw from moving back and forth in all the axes. These little shaft collars, because they're anodized, they went ahead and anodized the threads as well for the set screw, and I had to take an M5 tap and kind of run it in there to get a little bit of that out, so my set screw would actually come in and come in contact with the lead screw itself. No big deal there. Extra collars. Got the extra collars. Okay. We'll talk. Okay. The limit wires. The way I'm going to run is I'm going to run two limit switches on each axis in series and use normally closed contacts. And so over at Osnest, they recommend that you kind of just tuck all your limit wires down in this slot on the top of this extrusion. But if you have T-nuts in the slot, you can't get the wires underneath the T-slot. And I went ahead and added a few extra T-nuts here in case I want to mount something on this back side here. In the original design, they have the motor controller back there, but I'm going to have that elsewhere. But I left some extra functionality in here as well. So I can't really run the limit switch wires in the slot. However, this 2040 extrusion has a hole right down the center of it. So I'm going to drill 2 holes in these Y-axis gantry plates so that I can run my limit wires down the center of that extrusion. I won't interfere or affect the rigidity or the strength of my Y plates at all, and I'll still be able to have a really good attachment for this 2040. So I recommend to the builders just put an extra couple holes in there so that you can actually use the channels themselves to run some of your wiring. All right, motor heat. So I can run this thing all afternoon. This motor doesn't get that hot. I mean, it's probably, let's say, 100 degrees maybe. It's not very hot. I mean, you see I've got my hand on here and I'm holding it pretty tight. And most of that heat is back here on this back plate. This is where they have all the heat sinking for their switch drivers, for their H bridges and all that. And right now it's on. It's been on for, I don't know, 20 minutes or so. Idle, with just sitting here, is drawing about 180 milliamps. I have my old ammeter here, and it's full scale at 1 amp. So we're right around 200 milliamps. Okay, talked about that, the motor heat. All right, I found out that, I learned kind of a valuable lesson. You should take your time when you're building your Workbee, and you should actually follow the instructions. So I ignored both Matthew's build video over on Openbuilds, and I ignored the OzNest printed assembly instructions. And I just went ahead and started building. I mean, come on, really. Well, that was a mistake because I ended up taking this thing apart quite a bit because I wasn't thinking ahead. I was more anxious about getting this thing to move than thinking about actually having a machine functioning when I get done. So I've taken that gantry plate off at least 10 times. And I've taken the Z plate off at least 6 times. And so I got some recommendations on the Z plate, which I'll talk about when I get over to the computer. I will say this. I've taken it apart so much I'm not afraid to take it apart because it goes back together really nice. And it's still secure and it's still all very... this thing is well engineered and it fits together really well. So you can just take the plate off and pull it apart. Now, I had the luxury of doing that because I hadn't built the whole thing yet. If I'd had the frame, then I'd have to take the frame apart to get the gantry off. And I don't even have the gantry on the screen. Hold on a minute. Come on, baby. Yeah, I'm going to take 6 of this dang video. This camera ran out of... The camera ran out of storage space and didn't tell me. So anyway, so I've taken that plate off, like I said, about 10 times. Goes back together great. Not afraid to take it apart. Works fine. Taking the Z-axis plate off a lot. You want to kind of build it in order. And because I didn't do that, I ended up having to take it apart again and actually build it in order. And I do have several comments about the Z plate attachment to the X here, and some extra things. But the other thing that you want to think about if you're doing your build is you want to think ahead of how you're potentially going to use it. Is there something that you may want to add to this? Like say I want to add a USB camera to one of these gantries. Where do I put it? Or I want to hook something onto the extrusion itself. So after taking it apart several times, I decided to put some extra T-nuts in my slots for things I hadn't thought about. And that's a good thing because I ended up moving my limit switch from this piece over here up to the C-beam. And, I'd take that end off, put some T-nuts in here as well. And these T-nuts that I'm using, they're the flat ones. They're not the one. Sure, later, if you want to add something, you can just put it in the ones that twist. Those ones, I think, end up being about 4 to 5 times the price of these flat ones that are just, threaded. So I put in a little extra ones. And that's where we are. So I got my lock collars on. I got it all together. I got the Z motor in. I do not have my my wheels loaded yet, so it is kind of got some some play to it in 2 axes, which is fine. It's as loose as it can go, but we'll go ahead and show you some performance here. and because I know that that's really what you want to see. So what I'm going to do here is I'm running a universal G-code sender over here, and I got a straight Arduino board with a screw shield running in here. Remember, this has got a motor driver built into it, so I can wire it directly from the Arduino. And these inputs in here to control this thing are optocoupled, so we don't have a problem with any kind of ground loops or any kind of potential voltage spikes, because they're internally optocoupled. And they actually run down to, I think I'm running this at 5 volts. So I don't know if these couplers will work at 3.3, but they certainly work at 5 all the way up to 28 volts, like I said. Oh, the other thing I replaced was, I was doing all my testing with 24 volt 1.7 amp power supply. Well, I'm over using the real power supply now. It's a 36 volt 17 amp power supply, and I plan on running the whole thing on 36 volts. Okay, so let's go ahead and we will home this baby. And I'm running, I just downloaded from GitHub. I cloned the repository, and I modified the config file so that when you do a homing sequence, it only homes in X for the moment. So I'm going to go ahead and home it. And I'm running this thing over here, I think on, I don't know, where did I end up putting it? It is on 1600 pulses per revolution. Okay, so I've just got it homed, and I've learned a lot about Gerbil, unfortunately. So anyway, we'll go ahead and run it back out about 10. All right, so I'm at a feed rate of 1,000 millimeters per minute, and I'll go ahead and run it out to 100. All right, so that's pretty good. Oh, I'll tell you what the current is. I'll run it back. I'll tell you what the current draw is. So we are about 260 milliamps when we're running at this rate. And again, I don't have a router connected to it, so it'll be a little bit more, and I'm actually not pulling it through a piece of wood or something else. So, our current may go up. But that's 1,000, so I'm going to go up to 5,000. I have my max velocity set at 10,000 millimeters per inch, which is hauling ass. All right, here's 5,000. I'm going to go up to 100. All right, I'll come back. All right, the current when that's happening is about 750 milliamps. Okay, I'm going to go out 500. I'm going to go out at 7,500 millimeters per minute. We're up here around 700, again, 750 milliamps. All right, so that's pretty good. It's probably faster than you'd want to wrap it anyway, but I know you're all interested in it. I'm going to go to 10,000. I'll go out to 10,000 here, just to show you what it can do. All right, this is up to about 800 milliamps now. I'm going to go ahead and come back. All right, so this is where a valuable lesson I learned is, one, was build it in order, and two, don't screw around with this rapid testing, so to speak. This thing does actually go faster. I'll tell you why I don't run it any faster now. I was screwing around with this before I got limit switches in and got everything set up right, and I ended up slamming this my X plate into that end, and that ended up torquing and actually twisting my lead screw. Not twisting, bending. I have a bend in my lead screw, and so this particular lead screw's got a wobble in it. I'm going to take it out, take it over to a granite table, and kind of try to feel where that bend is. I tried to kind of fix it in the machine, but that's probably not a good idea. You end up flexing too many of the bearings. So I'm going to fix that. But you know, there's two morals to this story. Don't screw around with rapids until you got your lead switch, your limit switch, your limit settings, and your soft and hard limits enabled, and verify all that before you start cranking up the speed. I was more interested in finding out how fast this thing was really going to go. And the other thing is, I had the enable keyboard movement on, and I ended up hitting the wrong key, and that's what ended up slapping into that end. So don't do that. Learn from my mistake. Yeah. So let's go ahead, and I'm going to show you. I got over here, I have a dial indicator hooked in here, and it's got one of these magnetic bases, but this is all aluminum, so it doesn't stick to that. So I actually mounted I just hand mounted a fender washer right here that the magnetic base will hook onto. So what I'm going to do is I'm going to switch over to another shot, and I take this thing out, in and out, like, I don't know, maybe 5 and 50, and then I run it all the way out, going pretty rapid, maybe 5,000 millimeters per inch. And you can kind of see that it comes back and hits exactly where it left from. We'll switch to that, and then after that, I'm going to go and talk about the computer, some design changes that, either the Osnes people or on the next run of your plates Openbuilds, you may want to make a few modifications to some of these things that I found so far. They're pretty simple to do, I think, and it would be a lot easier to actually do maintenance on this thing in the future. So let's go over to and look at the dial indicator test that I ran, and then we'll go talk about the computer. We'll go do our CAD work, and I'll show you some stuff there. So I got my dial indicator kind of zeroed out, and I got the speed at 5,000 millimeters per minute. That's about a millimeter. Here's 10 millimeters. And here is 100. And then here is about 500. And we're back to 0. And you can hear that lead screw kind of making a lot of noise. All right, I have the Workbee CAD model open in Onshape. And we're looking at the right Y plate here. And this is where I suggest you put a hole right here. That way, if you have limit switch wires, you can run them down the center of the back of this 2040 extrusion. All right, that's the first thing I'd change. You can see over here I was playing around with where to mount those limit switches. I'm not doing it exposed like this. I'm going to rotate it around and have it down in this area here for the Y-axis limit switch. Okay, second thing is, if we were to come in here and look at the way that the Z plate is mounted to the X plate, it's a sandwich design, and if you look at the back, let me isolate this piece here. So this part here is the Z plate, and it uses these low profile M5 screws, and they're recessed in this kind of pocket back here on the back side, and then the whole thing is kind of sandwiched together. Once you get this together and you put on, once you have these things affixed there, these particular screws here are for the wheels, and you can't get access to these screws at all. So that's a problem. You can't get access to tightening these, which is fine. You don't need to tighten those. But if you want to take the X plate off, you can't get to these screws that are holding this thing together. There's actually 8 holding them together. There's 4 here. And let me hide this guy. And there's 4 back here. All right, so you can't get to those if you have the X plate on this extrusion, because you can't get through. I mean, you can't get your screw on the back side of this thing to get access to those screws. So you got to take the whole X plate off to get this plate off. And so my next suggestion is, if you were to thread holes on the back side of this, on the X plate, and just have your low profile M5 screws go from the front into this plate without actually having a retaining nut, you could get the Z plate off without having to take the machine apart. Okay, that's a good thing. There's a nice feature about this that I want to kind of show you here. If I want to hide this guy. All right, so when you go to tighten these screws back here to hold the Z plate on, the geniuses involved at doing this plate design knew that you were going to have these 2 plates hooked together already in terms of the wheels and everything. So you already have this assembled. So they put some access holes on this plate, so you can put your hex driver into this hole to get access to that screw. And that is actually that's a nice feature. Let me just get normal to here. So you can kind of see through there. That's the back side of the screw. You can get all the way through there. However, they figured all this out, and that's great. But what they didn't figure out, which is unfortunate, the next fix I suggest you guys make is, let me hide this part here. All right, this Delrin block that is on the Z lead screw has the holes, there's socket holes here to hold the nylock into this block. And then the way you tighten these is before you put the plate on, you have to tighten down these screws. All right, well, you can't really check the position of this thing. Well, it's just kind of, you got to build this correctly in the right order to get this thing in the right position for the lead screw to go all the way through. And this thing does have a little bit of play when these screws are loose. You can move this around a lot. So you have to kind of put together the C-beam has to be in here with the bearings, and the lead screw and all that have to be in here in order to get this guy in the right place to tighten the screws to come in from the backside of, you can't adjust this thing after you have these mated, because there's no access holes on the plate back here to get access to these 2 nuts up in the front. So there's 2 things I'd recommend. If you're going to thread this back plate, you might as well thread this plate as well and front mount this thing with screws down in from the front. And I know that these nylocks kind of protect all this from moving around. And that's an issue. If you don't want to do that, then at least put access points, just like you did with these other holes, in the center of this plate, in the center of that plate, so that after you get them mated and you got it all ready to put together, you can actually tighten this block down. Okay, that's pretty much what I have here. And you kind of see, in order to let's say you want to do some maintenance on this plate, you have to take off this piece here. You have to loosen this. Then you have to take you have to take these plates out, this plate off with this thing already attached. So you have to disconnect this whole thing. And that requires that you take this free with this bracket on the front side and the back side. All right. Then you could pull this whole side off. Then you could slide this off of that rail. And then with that there, you can pull the Z-plate off. All right, so that's quite a little bit of activity there. Now, I did mention that I was to think ahead. And so what I did do, like I said in the previous time before, was I made this screw here. This is a 20 millimeter M5 screw. I made it 30 millimeters, so I have 10 millimeters of extra shaft sticking out, so that when I did I break this thing? Oh man, there we go. So I am going to be able to attach a my dust shoe to the Z plate and not have it move up and down with the Z axis. That way I can have it at fixed height off of my workpiece. All right, let's go back into the workshop. All right, well, let me wrap it up here with a couple of topics. If you're going to build one of these things, think ahead. What are you going to use it for? What kind of features could you add to it now to keep it from having to tear it apart and to add something that you haven't thought about? For me, there's a couple of things. I put this T-nuts in. I also put in some screws for my dust shoe attachment. So if I hadn't thought about that, adding those screws afterwards would require that I take the frame apart, I take the end off, I completely take this plate off, run it off, take the whole thing apart, put those screws in, and put it all back together. Now, I've done this so many times, I'm kind of confident I could do that, and it would go back together really well, but that's not the point. Just think about what you'd like to do about it, and just, give it some thought. Okay, in that, from that respect, the other thing major thing I learned was build it in order. There's a reason why, Matthew, and the written instructions from OzNest are written so that you can build it in order. Particularly with that Z plate, you need to build that first. You need to put it all together because you can't do it afterwards. You can, but it's going to require you to do a lot of disassembly to get it all together. Because of my slamming incident, I learned a couple things. Don't rush what you're doing. I mean, enjoy this. Take your time. Do quality work. And I know you're excited. I'm excited. I want to get this thing cutting things for me. I'm actually on a journey to Tonehenge. This is a tool. So I want to get it right. The major thing is if you're going to test rapids, only do that after you have the limit switches installed, configured, and tested. Got that? Do all that stuff. Don't shortchange that. The other thing is, don't enable this keyboard movement convenience over here on Universal G-Code Sender, because I guarantee you'll hit the wrong key and slam your axis into the end, and hopefully you just will have skipped steps. But with this beast, you don't have that. This beast torqued my lead screw, and now I have a different problem that I'll have to resolve here in the near future. All right, thanks for watching. This is the Valve Studio.